Our next topic that is closely related to Lewis structures is the idea of resonance and what it means for electrons to be delocalized. So let's start by drawing the Lewis structure for ozone. So ozone is O3, so one of the oxygens is a central atom, and the other two oxygens are arranged around it. The number of valence electrons, 3 times 6 for a total of 18. So I'll give single bonds to all the atoms that need to be connected. Then I'll start giving electrons as lone pairs to the non-central atoms. The two oxygens are the same, so it doesn't really matter which one I start with. So I've used 2, 4, 6, 8, 10, 12, 14, 16. So the two outside oxygens have complete octets. I have 2 electrons left for 18. And then I check the 2 non-central oxygens have complete octets, but the oxygen in the central oxygen atom does not. It only has 6 valence electrons. And so in the previous video I said it doesn't matter which one I take it from. It turns out that's not exactly true. We could do it from either one. And so we could draw that Lewis structure, or we could draw this one. Now, what this might lead us to believe is that an ozone molecule has one double bond and one single bond, or that it's flopping back and forth between the double bond being here or the double bond being here. And it turns out that's not the case. So when we have this situation where there are multiple ways of arranging the electrons so that all of the atoms have a complete octet, like we had in the case of ozone, the actual structure of the molecule, so what the molecule actually looks like, is a hybrid or a combination of all of the different possible structures that we call resonance structures that we can draw. And so we would say that these 2 Lewis structures that we drew for ozone are 2 different resonance structures. But neither one accurately describes the actual ozone molecule. It turns out the actual ozone is a compromise or a combination of these 2, where each bond is a 1.5 bond, not a single bond or a double bond. And so the example that I like to use is like when you're breeding animals, right? If you have a Labrador Retriever and a German Shepherd and you mate those and have puppies, you don't get half purebred German Shepherds and half purebred Labrador Retrievers, right? All of the puppies are going to be a combination of the 2 breeds that you bred together, right? They're not German Shepherds and they're not Labrador Retrievers. They're a hybrid of those 2 breeds. And so the same thing is true here. I don't have a double bond here and I don't have a double bond here. The actual molecule is the hybrid or the combination of those 2, where I have 2 1.5 bonds. And the molecule doesn't flip back and forth between these 2, just like these puppies don't flip back and forth, one second being a Labrador Retriever and the next second being a German Shepherd, right? All the time, they're a combination of the 2 breeds. And so resonance structures are what we have when we have multiple ways of arranging the electrons to achieve an octet rule, and each Lewis structure that we can draw that satisfies the octet rule is called a resonance structure. The actual molecule looks like a hybrid, or it's a resonance hybrid of all those Lewis structures that we can draw. And so these electrons that are moving around in the different Lewis structures, or they appear to be moving around, we say that they're delocalized. So the electrons are spread out. They're not localized. They're not concentrated between any 2 of the oxygens. They're spread out between both types of bonds. And so when you can draw resonance structures, the electrons that are moving around, or they appear to be moving around when we draw the different resonance structures, those electrons are said to be delocalized. Now, one of the reasons we care about this is because resonance is a stabilizing effect in molecules. When molecules can have different resonance structures, they do because it lowers their energy. They like to spread their electrons out. So having multiple resonance structures or having this electron delocalization is a stabilizing effect. It lowers the energies of the molecules, and so they like to when this happens. All right, as an example, let's draw the resonance structures we can for the carbonate ion. So carbon is the least electronegative atom, so it's going to be our central atom. So we'll have carbon, nope, try again, carbon, oxygen, oxygen, oxygen. For our electrons, the carbon is going to give us 4. Oxygen is going to be 3 times 6, because I have a -2 charge. That's going to give me 2 additional electrons. So that's going to be 24. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used all my electrons. The oxygens are all happy. Carbon doesn't have a complete octet, so I'll need to take one of the lone pairs on one of the oxygens and convert it into a double bond. So I'll take those, make it a double bond. So that's one possible resonance structure. But then I just as easily could have taken the lone pair from that oxygen or the bottom one. Now each one of these has a -2 charge, so we'll put them all in brackets with a -2. And then typically when we draw resonance structures, so in this case carbonate has 3 resonance structures, we use double-sided arrows. And so we say, okay, to indicate that we're drawing resonance structures and that the actual molecule is a combination or a hybrid of all 3 resonance structures, we will typically draw those double-sided arrows between them. So if I said draw all the possible resonance structures for the carbonate ion, this is what you would want to draw for me. Okay, our last example is HN3. And I've written the formula to try to indicate that the way these atoms are connected is a linear, well, at least we have this arrangement of how the atoms are connected. Alright, so for my valence electrons, hydrogens are going to contribute 1, nitrogens 3 times 5, for a total of 16. I've used 2, 4, 6. I'll start giving electrons to the outside atom. 8, 10, 12. Now for the 2 central nitrogens, since this is sort of more of the outside, I'm going to put them here. If we'd made a different choice and put the 2 lone pairs on the central nitrogen, that wouldn't necessarily be wrong, but it's going to be harder to get all of the resonance structures. So I've given out all my 16, 2, 4, 6, 8, 10, 12, 14, 16. And of course that nitrogen in the middle does not have a complete octet. It only has 4 valence electrons. So I'm going to need to convert 2 sets of lone pairs to bonding pairs, but I have a number of different ways that I can do that. So let me use a different color here for these. So I could take both lone pairs from this nitrogen, in which case I would have a triple bond there, in a single bond, but everybody has complete octets. Or I could take both lone pairs from this nitrogen and convert them into bonding pairs. In that case, our Lewis structure would look like that. Or I could take one lone pair from this nitrogen and one lone pair from this nitrogen and get a third possible Lewis structure. So in this case, we have three possible resonance structures for this molecule.